Alright, in this video we study the limit of a univariate function. A univariate function means a function of one variable. Say we have a function f of x, and if this function approaches some constant alpha as we move x towards a, then we say this f of x converges to alpha as x approaches a, and we write limit of f of x as x goes to a is alpha. So in the following, we make the meaning of this limit more precise. Okay, let's start. Okay, to begin with, what do we exactly mean when we say the value of f of x approaches alpha? So by this, we mean that the difference between f of x and alpha becomes 0. So it gets closer and closer to 0. And similarly for this one, when we say x approaches a, that means the difference between x and a is converging to 0. Well, of course, we haven't defined convergence yet, but the meaning will be clearer later. So given this intuition, we define this limit of f of x is alpha as x goes to a by the following. Okay, here's the definition. That is, for all epsilon that is positive, there exists some delta that is positive, such that for all x in the domain of f, if the difference between x and a is less than delta and greater than 0, then the difference between f of x and alpha is less than epsilon. If this holds, then we say the limit of f of x is alpha as x approaches a. So here's the definition. In this definition, of course, we implicitly assume that epsilon and delta are both real numbers, okay? Positive real numbers. Okay, let's visualize the meaning of this definition. So suppose we have some function, let's say this is x, and we plot this function. Let's say this is f of x, okay? And suppose this is alpha. And take any epsilon, okay? So we want to make this hold, okay? So let's say if we take epsilon, so this will be alpha plus epsilon, and this will be alpha minus epsilon. So this interval, this size is epsilon. So we have this interval in the y-axis, and if so, this is a, and if we make this interval small enough, then the difference between f of x and alpha is small enough. Okay, so if we take this as a minus delta and a plus delta here, so as long as x, the value of x stays in this interval, then the difference between f of x and alpha stays inside this interval on the y-axis. Okay, so if x is somewhere here, then it should be somewhere here. So the value of f of x is within between alpha minus epsilon and alpha plus epsilon. Okay, so that's what we mean by this definition. So if we take delta small enough, so if we take small enough interval, then the whole interval stays within this interval. Okay, so if this can hold for any value of positive epsilon, then we say the value of f of x converges to alpha. Okay, let's see a concrete example. Consider this simple function f of x equals to x squared plus 1. Now let epsilon be, say, 0.1, 0.1, and let's find the value of delta that is positive, such that if x minus, let's say x minus 1 is between 0 and delta, then the difference between f of x and, so let's say 2, is less than epsilon. Okay, so if epsilon in this case is 0.1. Okay, so to begin with, let's suppose this holds. So we should have x squared plus 1 minus 2. Absolute value of this should be less than 0.1. Okay, from here we have negative 0.1 less than x squared plus 1 minus 2 is x squared minus 1 less than 0.1. So from here we have 0.9 x squared and 1.1. So taking the positive side, let's see, we have square root of 0.9 x and square root of 1.1. Okay, we take the positive side because we are approaching x towards 1, so positive 1. So it should be closer to positive 1 than negative 1. And square root of 0.9 minus 1, remember we are approaching x towards 1, and this is approximately negative 0.0513 and so on. And square root of 1.1 minus 1 is approximately 0.0488 and so on. So if we compare the absolute values of these, this one is smaller. Okay, so let's say if we put x minus 1, absolute value of this, less than square root of 1.1 minus 1, then if this holds, then we can say that x1 squared plus 1 minus 2, its absolute value is less than 0.1. So we can find such a delta. So if we put this as delta, then we can make this inequality hold for epsilon equals to 0.1. In this way, we can always find some delta for any positive epsilon. Say if we said epsilon equals to 0.01, then we can find some appropriate delta accordingly. And this happens to any epsilon, as long as it's positive. So in this way, we can prove that the limit of this function as x approaches 1 is 2. So the limit of this function as x goes to 1 is 2. So it is a good exercise to find some general expression for delta without specifying concrete values for epsilon in this case. So that means, can we find some delta such that if x minus 1 is less than delta, then x squared plus 1 minus 2 is less than epsilon for any epsilon. Okay, so find a delta, find this delta as a function of epsilon. So it's an exercise. This may be a little bit difficult, so let's consider a simpler example. Consider a linear function that is f of x equals to 2x. And let's show that this limit to the limit of 2x as x goes to 1 is 2. This is obvious, but let's actually prove this by using the epsilon-delta argument. Okay, so let epsilon be any positive real number. Okay, then define, if we define delta as let's say epsilon over 2, then if x minus 1 is between 0 and delta. Then we have f of x minus 2, its absolute value, as 2x minus 2 equals to 2 this. And we're assuming this, so this is less than 2 times delta. But delta is half of epsilon, so that is so this is equals to epsilon. So if we set delta like this, then we certainly have, if this is true, then the difference between f of x and 2 is less than epsilon. So that means for any epsilon we can find an appropriate delta. Therefore, this the limit of this function is 2. Alright, that's all for this video. And in the next video, we study some basic properties of the limits of functions. See you later.